I will be explaining continuity of measure. Okay, name of the theorem is continuity of measure in this video. This is a named theorem, so you have to learn the statement also. Lebesgue measure possesses the following properties. Okay, that is continuity of measure. The statement of continuity of measure is Lebesgue measure possesses the following properties. Continuity properties. These two properties. Who is possessing these two properties? Lebesgue measure. Okay. The first one is if a sequence is given. A collection is given. Sorry. If k equal to 1 to infinitive is an ascending collection of measurable sets. They are saying they are measurable sets. They are the collection of measurable set and also they are arranged in an ascending order. A1, A2, A3. They are in ascending order. Okay. So that is what they are written. It means it is like this. A1 is this. A2. Ascending means what? Small to big, no? So it is going on like this till what? A infinitum. That is what they are saying. So if AK is the collection of ascending collection of measurable sets means then this condition will be there. That's the first property. And if BK k equal to 1 to infinitive is a descending collection of measurable sets and another one condition is also given. Here these are the measurable sets and they are arranged in how? Descending order. Okay, descending order means what? Big to small. That is B1 will be like this. Inside B1 you will have B2, B3, B4 goes on like that. So here a condition is also given. They are given measure of B1. You are having this B1, no? Measure of this B1 will be less than infinitive. It means what? Measure of this B1 is finite. That is what they are saying. So if these conditions are there, then this condition will be satisfied. These are the two properties of what? Continuity of measure. So here, let's start proving the first part first. Okay, first part. To prove, write this, copy it, okay? Measure of union k equal to 1 to infinitive ak is equal to limit k tends to infinitive measure of ak. Okay, write this. Now, we are having two, okay. If m of ak, if measure of one measurable set, that is ak, okay? You are taking one measurable set, ak, and you are taking measure of it. So, yeah, if measure of ak is infinitive means it's trivially satisfied. That is, this condition will be trivially satisfied. Okay. Then, when it will be satisfied, measure of ak equal to infinitive means if measure of ak less than infinitive, it means this is another one case. Okay. In case one, in this case you are having no proof. You just write the result is that it is trivially satisfied. That's enough. Here, in another one case, if m of ak less than infinitive means, it means if measure of a measurable set ak is finite means what you have to do is first you are defining this. Define a not equal to mt. You are defining these, okay? To prove this, you are defining. Okay, define a not equal to mt. And also you are define ck is equal to ak difference ak minus 1. Okay, keep this in your mind. Also, since the sequence this is ascending, in the statement you are having ak k equal to 1 to is ascending. So, when you find the sequence of this ck k equal to 1 to infinite, that will be disjoint. That is, when you find c1, what do you get? a1 minus a0. When you find c2, what you will get? Substitute in the place of k, you are putting 2, right? So you get a2 minus a1. Similarly, you do for c infinitive. Okay. So what you are coming to know from here? Look at this c1. You are subtracting a0 from a1. Look at this c2. You are subtracting a1 from a2. It means if you do this subtraction, then in C1, C2, C3, you could not find any common elements. There will not present any common elements. So if there is no common elements, what will happen? The C1, C2, C3, these will be till C infinitive. They will be disjoint because there is no common elements. So that is what you are writing. Ck k equal to 1 to infinitive is disjoint, and you are saying when you find the union of this you will get a value, no, that will be equal to the union of the ck. That is how you are writing. You will get like that, okay? The union of this AK will be equal to union of this CK. When you find the union of C1, C2, C3, C2, union of that, you will get a value that will be equal to this. That is what you are writing. Now, you are taking measure on both sides. So, you will get this. And after that, you are using what? You are having, I think the name is, using a proposition you are writing, countable subadditivity. Okay, using a proposition from this step to this step you can write, that is union is becoming summation k equal to 1 to infinitive and measure is coming inside, so m of ck. How you are writing? You are using like in this format by a proposition. Now in the place of ck you substitute this ak difference ak minus 1. So you will get this. Now summation k is equal to 1 to infinity. You are multiply m to these two terms so that you will get m of ak minus m of ak minus 1. Now you are making an adjustment here. Summation k is equal to 1 to infinitive can be written like this. Limit n tends to infinitive. Summation k is equal to 1 to infinitive. Here n tends to infinity. The same thing you are writing like this with an adjustment. So m of ak minus m of ak minus 1. Now you are expanding it, okay? You are putting the value of k equal to 1 and then k equal to 2, k equal to 3, summation. So you are putting plus 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 in between. So here limit n tends to infinitive, write this, and here you are expanding. First put in the place of k you are putting 1. So when you put 1, what do you get? M of a1 minus m of a0. Okay, and then summation, no, so plus. Then put k equal to 2 so that you will get. Similarly, when you put k equal to n, you will get this. So what will happen is the terms, most of the terms will get cancelled. This and this will be cancelled. A2 and m a2, and you will get somewhere you will get minus minus m a2. So this will be cancelled and this will be cancelled. So remaining you will have only these two terms. So you are writing in that in the next step. Limit n tends to infinitive m of an minus m of a0. Now from here you are having in the first line of this case you defined a0 equal to mt. No, so here a0 equal to mt means measure of a0 equal to measure of mt. Measure of mt set is 0. Okay, so that is why this becomes 0. So you will get this. Now you are having this in the statement. You are not having, you are having limit k tends to infinitive m of ak, but here you are having n. So what you are doing is you are just converting n, okay, replacing n by k. Okay, in the place of n you are putting k. Okay, so that is how you proved the first part. Now let us pass on to proving the second property. So to prove the second property, you are defining this dk is equal to b1 difference bk for each k. Okay, don't forget this is important. Now since bk k equal to 1 to infinitive is descending sequence, in the statement itself they are given. So if this is descending sequence, then dk will be ascending, this will be ascending. That is when you find d1, the place of k, when you put 1 you will get b1 minus b1, you get 0. When you find d2 you will get b1 minus b2. So this is a descending sequence, no? So when you find d1, d2, these values like this, here you will get the answer values, no? Values will be keep on increasing. Okay, the number that comes after 0 will be bigger than this 0, and when you find d3, that value will be bigger than this. So it will be in ascending order. So that is why since bk k equal to 1 to infinitive is a descending sequence, this dk sequence will be ascending. So this is ascending sequence. Now you know that if there is an ascending sequence, in the first property you told if there is an ascending sequence means is ascending collection means this condition will be satisfied, you know. So that is why here is also you are having dk is ascending. So that is why you are using part 1 for dk. Okay, so from part 1 we write this. In the part 1 you are having ak, here you are writing for dk, no? So that is why in the place of ak here you are putting dk. Now what you are doing is you are going to find the value of this first, and then you will find the value of this, and then you will substitute the value of these two in equation number 1. So that is what you are doing. Now measure of, just write it, is equal to measure of this, in the place of dk you put the value. Okay, you define like that. No, dk equal to b1 minus bk, so just write it. Now measure of this can be written like this by De Morgan's identity. Using De Morgan's identity you can write like that is, first put b1 difference, union becomes intersection, k is equal to 1 to infinitive, and then this. How you are writing this? You are writing this by the De Morgan's identity. Now we are going to find the value of m of dk. So you have dk equal to b1 minus bk. So from this you are taking measure, so that you will get this. Is that clear? So you found m of dk also. Now what you are doing is you are substituting this and this value in equation number 1, so that you will get this line. And now what you are doing is you are multiplying limit k tends to infinitive to both the terms. Here you are not putting limit m tends to infinitive here. Look at this, you are multiplying this. So m of b1 minus m of this value is equal to, here you are not putting limit k tends to infinitive m of b1. The reason is because m of b1 have, here you are not having any k terms, right? So that is why here it is not necessary to write limit k tends to infinitive m of b1. So that is why you simply wrote m of b1, okay, without this limit k tends to infinitive. Now here you are writing limit k tends to infinitive m of bk, because you need limit k tends, you are having a purpose for this limit k tends to infinitive for this term, right? Because you are having k here, no, here you are not having k, like that is why here you are not writing limit k tends to in this step, but here it is needed. Okay, I hope you can understand, because it's very simple. Now this and this get cancelled, and minus also will get cancel. So remaining terms is our this is what we have to prove in the end of this property. End of the property you have to prove this, right? So you proved it, hence the proof.